everybody. In last day, I discussed a little bit about the technique of finding the evaluation of the area under a curve. And in my previous discussion, the mainly the curves we considered in our previous class is in the Cartesian form. Hmm. Particularly y is equal to fx or x is equal to phi of y. This kind of curve we considered. Today, I shall continue my discussion and hopefully within today this chapter will be finished. Hmm. Today, I shall discuss about the parametric curves and how to find out the area under this kind of curves. Okay, so a parametric curve. We know that a parametric curve, that means a curve which can be written in this form: x is equal to phi y and y phi of t, and y is equal to phi of t. This kind of curves are actually parametric curves. For example, if you consider a circle, generally circle parametric curve of circle with radius small a, this parametric curve can be written in this way: x is equal to a into cos of t or theta, and y is equal to a into sine of theta or sine of t. Okay, so theta or t, these are the parameters. This t is parameter over here, and a is the radius of the circle. In that case, if you square these two expressions and add them up, you will get the Cartesian equation: x square plus y square is equal to a square. The Cartesian equation of the circle with radius a. All right. So over here we are going to consider this kind of curve. There are certain curves which are represented mostly in parametric form. Hmm. And we shall have to find out the area under this kind of curves. All right. So over here, x is equal to phi of t, y is equal to psi of t, and we know that the integral of the representing the area, that is actually the integral from a to b f of x dx, this kind of curve. Hmm. Y is equal to f of x dx. Okay, you could also consider this f of x. In place of f of x, you could write y into dx. Okay, now this y, in place of this y, we can put this expression of y, and then if we put y is equal to psi of t, you will get this kind of expression. This is y is equal to psi of t. And what about dx? This dx can be written in this way: phi dash t into dt. Got it? Therefore, we have this kind of representation of the area under this curve: integral psi of t into phi dash t dt. Now the question is that how to find out the limits t1 and t2 in terms of t. Okay, and in order to find out the limit, your question would be a hint to find out the limit. For example, consider this one, example number 6. What is this? It says that the area bounded by one arc of the cycloid x is equal to a into theta minus sine theta, and y is equal to a into 1 minus cos theta. This curve is actually this curve is actually called cycloid. This is the cycloid, and this is actually the picture of the curve. In this kind of curves, generally this cycloid is symmetric about the middlemost point. Hmm. And this angle is considered as the angle theta. With respect to this angle, the x and y coordinates of any point P, if you consider any point P, on this curve with coordinates x and y. Okay, with coordinates x and y, then x has this kind of representation and y has this kind of representation in terms of the parameter theta. Hmm. And what is a? Actually, if this kind of curve is actually generated by the rotation of a cycle tire, or you can consider by the rotation of a circle. That's why related to cycle tire we have the name cycloid. Hmm. And if we rotate this kind of circle, and with this point, fixing this point, and if you rotate the position of this circle, then after rotation the the locus of this point actually constructs this curve, that is the curve cycloid. Okay, this much I am saying because I am not going to deduce this curve. Hmm. But how to know the area, how to know the lower and upper limit of theta, because in place of this parameter t, over here the parameter is theta. Okay, so in place of t1 and t2 we need to know the value of the parameters. You can consider them as theta 1 and theta 2. Okay, then the question is that how to find out the values of theta 1 and theta 2. Let me answer this question over here. You see, actually the total one rotation will generate one segment starting from this point O to this point D. And total rotation means if you just rotate a single uh, circle, then you can cut any part of this circle, then the total perimeter, and the total perimeter is equal to, we know the total perimeter is equal to twice pi a. The area and the total arc length of a circle is equal to twice pi a, or the total perimeter of a circle is equal to twice pi a. So if we just rotate the circle one times, then we shall move at this much distance, twice by a distance. Then what would be twice by a? This much, the distance OD, O to the distance D, this OD, that should be is equal to this twice pi a. Got it? Therefore, it's half. That means half of this length, this much length. Hmm. This much length would be is equal to pi multiplied by a. Got it? So we can say that the coordinate, as because this much distance, this OD, this much distance is equal to twice pi a. Therefore, the coordinate of the point D, the x coordinate of the point D must be is equal to this twice pi a comma 0. We know that the y coordinate of any point lying on x-axis, this y coordinate is always equal to 0. Got it? So this would be the coordinate, and this would be the coordinates of the point D. All right, and if you see this this value x becomes is equal to twice by a. That means starting from the point O to the point D, starting from the point O to the point D, we will get this much length, and that is actually is equal to twice by a. Then what is the value of theta at the point D? What would be the value of theta at the point D? In order to find this and the answer to this question, you see, if we put over here, x is equal to twice pi a, x is equal to twice pi a, and y is equal to, what is y? Y coordinate of this point is equal to 0. So we are putting y is equal to 0. Got it? Now if we put y is equal to 0 in this expression, y is equal to 0 in this expression, then a into 1 minus cos theta, that would be is equal to 0. Hmm. A into 1 minus cos theta would be is equal to 0. What does it mean? It means that cos of theta, okay, this expression must be is equal to 1. Then what is the value of theta in this case? Hmm? Theta would be is equal to twice pi, because yeah, theta would be is equal to twice pi, because cos of twice pi, that is actually cos of 0, that is equal to 1. Hmm. So cos of twice pi, that is actually 1. Therefore, we shall get this value of theta. So theta would be is equal to twice pi. So if we put this value of theta, theta is equal to twice pi in this expression of x, you see, if you put theta is equal to twice pi, then sine of theta would be is equal to 0. And just putting theta is equal to twice pi over here, you will get the result x is equal to twice pi a. Got it? So theta is equal to twice pi. Over here, the value of theta, theta should be is equal to twice pi at the point D. Hmm. And similarly, at the starting point O, at this starting point O, what are the coordinates of the point O? 0, comma 0. The origin 0, comma 0. These are the coordinates of the point O. All right. So if we put over here, just similar to this fashion, if we put y is equal to 0, this coordinate y is equal to 0. So if we put y is equal to 0, again we shall get cos of theta is equal to 1, and in that case you see we will get one more value of theta. Then that value should be theta is equal to 0. We cannot take theta is equal to pi. Why? Because if we take theta is equal to pi, we'll get this point. However, if we put theta is equal to 0, you see over here, if we put theta is equal to 0 in this expression of x, hmm, in this expression of x, if we put theta is equal to 0 in this expression of x, you will get x is also is equal to 0, so that we will get the x coordinate equal to 0 and y coordinate is equal to 0. Therefore, we can say that theta is equal to 0 at the point O, and theta is equal to d, and sorry, theta is equal to twice pi at the point D. Got it? So in this fashion, we would be able to find out the value of theta. And for this kind of expression, the total integral can be computed in two different ways. One is the fact that we can integrate from theta is equal to 0 to theta is equal to twice pi within this kind of integral. Then we just put phi psi of t. What is psi of t? Psi of t is equal to this expression 1 minus cos of theta. That is actually the expression of y. Got it? And what is phi dash t? We can put phi t is equal to this expression, the expression of x. X is equal to a into 1 minus cos theta. So from this expression of x, we can find out the expression of phi dash t, phi dash theta. In the over here, the parameter is not t, so integration should be written in terms of theta. Therefore, we can write that we should have this kind of expression psi of theta, hmm, psi of theta into phi dash theta, hmm, into d theta. Got it? So in this way we can integrate. And one another technique to integrate is that you see this picture is symmetric about this middlemost point. Hmm. So if we find out the area of this zone, just from O to this middlemost point, the area of this zone, then it would be easy to compute the area of the total zone. Just multiply this area by 2, then you will get the total area over here. So you see over here, at the point theta, at the point O, theta becomes is equal to 0, and at this point theta would be is equal to pi. Okay, you can check this at this point, this middlemost point over here. At the right side theta is equal to twice pi, on the left side theta is equal to 0, and at the middlemost point theta would be is equal to pi. That's why if we simply integrate integrate this expression and just put integration from theta is equal to 0 to theta is equal to pi. Got it? And then afterwards just multiply this expression by 2. Even then you will be able to find out the area of this cycloid area, this total area under this cycloid. Got it? So in this way you can find out the area of under this cycloid. Okay, and in this total in this example, a deduction has been used. We don't need all these deductions. Okay, you can directly put the expression of y and the expression of dx, and over here, just in place of x, you see the limit of x should be is equal to 0, x is equal to 0 to x is equal to twice pi a. Why? Because the x coordinate is over here twice pi a. However, whenever the total expression is converted in terms of theta, you see the limit becomes theta is equal to 0 to twice pi. So after that, just it is a matter of computation. I discussed this process, the area included between two curves in the previous lecture, so I am skipping this part. The However, I am going to discuss this one or two example, because this kind of examples are important as far as the exam is concerned. Over here, we know that we are given that we have to find out the area bounded by two curves, y is equal to x square and x is equal to y square. So y is equal to x square and x is equal to y square. These are actually two parabola. One is this kind of parabola, y is equal uh, x is equal y square is equal to x, means this kind of parabola. And another x square is equal to y, means this kind of parabola. So we will have to find out the area of the region bounded by this kind of curves. Y is equal to x square and x is equal to y square. Now, if we solve these two curves, you will be able to find out the point of intersection of these two curves. So one point of intersection would be is equal to 1 comma 1, another is the point 0 comma 0. So it is not difficult to find out the point of intersection. Just solve these two questions and solve these two equations, and ultimately you will be able to find out the area under these two curves. Now, how to find out the total area? In that case, if it is possible to draw the picture, it would be very easy to identify the total area, how to obtain this area. You see, in that case you would be able to obtain the curve which lies on the upper side and the curve which lies on the lower side. These are the two boundaries. This curve O, B and the point P, the part of the curve starting from the point O to the point P through this point B. This is the upper portion, upper boundary, and starting from the point O to the point P through this point A, this is the lower boundary. That is the curve actually y is equal to x square and upper boundary is x is equal to y square. And over here, if we firstly find out the total area under this upper curve, this total area, hmm, is total area under this upper curve. If it is, if you integrate it, then you will be able to find out the total area by this kind of integration, integral of y dx. Hmm. And in that case, what would be y over here? Y should be is equal to, y would be is equal to the positive square root of root over of x, because in the upper curve y square is equal to x, and in the first quadrant x and y are positive, so we will have to consider this positive square root of root over of x. Y is equal to minus root over of x would hold for the second quadrant. Okay, all right. So no, not for second quadrant, for the lower quadrant, that means for fourth quadrant, this for this region, if any computation is to be performed in this region at all. Anyway, so we'll have to consider this positive square root of root over of x, and what would be the lower limit? Over here you see the lower limit should obtain from this x coordinate of the point 0, and the upper limit of x should be the x coordinate of this point p. So x should vary from 0 to 1. In this way, you will have to find out the area, total area under this upper curve. Now, from this upper curve, you will have to delete this area under this lower curve. Got it? You will have to delete the area under this lower curve. Then only you will be able to get this area shaded of the area of this shaded region. Then what would be the area that is to be removed? This area is to be removed. That means the area under this lower curve. So lower curve is integral from y dx, and in this lower integral, or the integral of this lower curve, the limits should be 0 to 1. Okay, and y dx, and what is y over here? Y is equal to x square. It is given that y is equal to x square. So over here you will have to put y is equal to x square. Got it? So if you put these results in this way, you will be able to find out this area which is to be removed. Now, how to remove this area? From this first integral, just subtract this second integral. Got it? Subtract this second integral, you will be able to find out the area shaded of this shaded region. So first integral minus second integral, that is the formula over here. You see, this is the first integral and this is the second integral. Lower limit is 0 and 0 over on these two integral, and upper limit is equal to 1. So just if you compute, you will get 1 by 3. Okay, and be very careful to find out the unit, whatever be the unit of the length. Suppose x and y are measured in terms of meter. In that case, the area should be written in terms of square meter. So that's why you don't know what would be the length, what would be the unit of x or unit of y. So that's why just you need to write 1 by 3 square unit. So in this way, you will be able to find out the area bounded by two curves. Okay, and similar such other examples are also given. You can go through these examples. Say this example number 3, though it is a bit difficult examples, and a few more examples are also there, but this kind of examples are very easy, and these are ideal for selection for exam. So please, if this kind of easy example comes in exam, please don't skip these kind of questions. And now I am going to show you another technique. You can go through this kind of questions over here. Say question number 1, A, B, and C. This one has already been discussed in this first case, and you see over here y y square is equal to 4ax or x square is equal to 4ay. These are very similar to the second question that I discussed, and this is actually the second question that I discussed today. Hmm. You can also discuss this kind of question number 3 or this question number 2. These are more or less easy questions and ideal question for selection in exam. We don't select much difficult questions. Okay, we generally select more or less standard questions, so you don't have to bother about much difficult questions. Hmm. You can even go through this question number 7. These are more or less easy kind of questions. Now, in this second portion, we will have to know how to find out the area of a curve if the curve is given in terms of polar coordinates. We discussed more or less different kind of curves. Sometimes the curve is given in terms of Cartesian coordinates. Sometimes the curve is given in parametric form. But if the curve is given in terms of polar coordinates means r, the radius vector, and theta, the vectorial angle. Hmm. So if the question is given in terms of polar coordinates, then how to find out the area under this kind of curves? Hmm. Uh, Good figure is already proposed over here. This is a technique by which they have computed the formula for evaluation of the area under this kind of curve. Say this is the curve, and its equation is r is equal to something like f of the function of theta. This kind of curves they consider, and starting from the first point P up to this last point Q, if suppose P has the vectorial angle alpha, this angle is equal to alpha, and if suppose Q has the vectorial angle beta, this angle, this total angle, hmm, this total angle, suppose this total angle is equal to beta. In that case, how to find out the area under this curve? This is the formula. I'm not going to discuss this deduction. You just need to know the formula. That's all over here. This is the formula. Half of integral r square d theta, where theta varies from alpha to the point beta. The lower limit of theta is alpha and the upper limit of theta is beta. Or if we put r is equal to f theta, in that case this integral can be written as integral from alpha to beta f theta its whole square d theta multiplied by half. Generally you forget this half. Okay, so be very careful about this half. Generally you forget to introduce this half. That is a common mistake that you perform in exam. As far as our experience is concerned, we get this kind of common mistakes. Okay, so you don't need to go through this deduction. Just try to remember this formula. And let me discuss one or two questions from by which we apply this formula. Suppose one curve is r is equal to a sine of theta. Hmm. This is actually the equation of a circle. R is equal to a sine theta. Over here it is mentioned that it's a circle. R is equal to not a. Actually, this is R is equal to twice a sine theta. It is actually the circle with radius a. Okay. So in that case, how can we find out the area of the curve? And for this kind of curve, you should have certain idea about the range of this kind of parameter theta. Hmm. Let me let me show you the technique. You see over here, theta. This parameter theta would vary from 0 to pi. How? Let me show you the picture. Hmm. Over here, this kind of circle. Let me draw the initial axis. This is the initial axis. Hmm. And let me draw circle over here. Okay, and this kind of circle, yes. Hmm. This would be the position of a circle, and over here, this kind of point, this point. Hmm. This point is a point on the circle, and if we consider any point P on this circle, P on this kind of circle over here, you see the radius vector. The radius vector is this one. Hmm. And what is theta? This angle measured in anti-clockwise direction. This angle is equal to theta. So when theta is equal to 0, this in this zone, this would be the starting position, and whenever P starts from this region and P moves away, then theta increases. In this region, theta would increase, and in this region, theta would be is equal to pi 180 degree. Got it? In the starting point, theta is equal to 0. Hmm. In the starting point, that means in this region, this is a very teeny region. Hmm. Let me magnify this picture a bit. In this region, theta is equal to 0, and over here, in this region, this theta would be is equal to in this kind of region. Whenever the whenever the point P would again come back and complete the circle over here in this zone. Hmm. Okay, it would complete the circle in this zone. In that case, theta would be is equal to pi. Okay, so that's why over here you would find that the range of theta in this picture, it is a bit hazy. In this picture, theta varies from 0 to pi. All right. So half integral from 0 to pi r square d theta. What is r? R is equal to twice a sine theta. So put the expression of r, and afterwards just perform the integration. This is the integration of 11 and 12 level. So I am not going to discuss the detailed calculation. Ultimately, you will be able to find the area of circle pi a square, and that is a well-known standard formula of computing of the area of a circle. So in this example, actually we are establishing the formula. How did we obtain pi a square? Got it? So this is the technique by which we can show that the area of a if area of a circle is equal to pi a square. Hmm. And one more example is there, that is for cardioid, very heart-shaped curve. Hmm. This is the cardioid. Hmm. And in this kind of curve, over here again you see P is this kind of point. This is the radius vector r, and this angle is equal to theta. So whenever P will have this kind of position, let me magnify this picture a bit. Hmm. Whenever P will have this kind of position, in this position, whenever P will have this kind of position or this kind of starting position, hmm, in that case, at the starting position, theta would be is equal to 0. Okay, and if the point P moves along this curve at this position, theta would be is equal to pi. All right. And again, further, whenever the point further moves along this curve, this is not the part of the curve. Okay, this is not the part of the curve. These are two circles just to demonstrate some properties of this curve. This is the curve. This is the curve. Okay. So whenever the point P further moves along this curve, and in this zone, whenever it comes over here, and this finally whenever it again touches the original first point, then theta becomes is equal to twice pi. Got it? and the area of this upper region, area of this upper region and the area of this lower region, both are same. That's why if we want to compute the area of under this curve, hmm, if we compute the area under this curve, then we firstly compute the area of this upper region, because the area of the upper region and the area of the lower region are same. Then but one area, you see, it lies on the upon the x-axis, and this area lies below the x-axis. So this much area would be the positive area and this much area would be the negative area. Got it? So if you want to find out the total area starting from theta is equal to 0 up to again come back to this position, and if you just put theta is equal to twice pi in the formula of integration, ultimately you will find that you get the total area is equal to 0. The reason behind it is that just this positive area and the negative area, they cancel each other. Okay, but we don't need to cancel these two positive and negative area. We need to compute the total area. So over here, theta varies from 0 to theta is equal to twice pi, and we compute the area of the upper region. That's why we need to integrate, we need to perform the integration from 0 to pi. Got it? R square d theta, and then multiplied by half. So whenever the lower limit is 0 and upper limit is equal to pi, we get the total area on the upper part of this curve. And if it is multiplied by 2, then we get the total area under this curve. Got it? That's why in this computation process, you see this 2 multiplied by half into 0 to pi r square d theta. Now if you put r is equal to 1 minus cos theta over here and compute this integral, ultimately you will be able to compute the total integral. So in this way you can compute the area under the cardioid. You can also find out the area under this kind of curve. R is equal to a cos of twice theta. You can compute the curve, and that would be this kind of curve. Over here you see, in this kind of curve, you just need to compute the entire area enclosed by the curve. That means this area, then this much area, then this much area, and then this much area. These are called rose petals, the name of these curves. Hmm. These are called rose petals. And how did you obtain this area, this curve? Actually, when theta starts increasing, when theta increases from 0 to over here at this position, theta is equal to pi. Then the point P moves from this point to this point, the origin. Okay, again when theta increases, the point moves from this position to this position, then from this position to this position, and then from this position to this position, and then from this position to again to this original position. So in this way theta increases. So over here in this first zone, let me magnify this one. In this first petal, hmm, at the point capital A, at this point, hmm, at this point, theta is equal to 0. Okay, and again, and when the point again along this curve comes to this origin O, then theta becomes is equal to, this is the directive lines, theta becomes is equal to, over here theta becomes is equal to pi by 4. Okay, theta becomes is equal to pi by 4. So over here,
Yes.
theta varies from 0 to 0 to pi by 4. Hmm. And this angle is actually this straight line is actually showing the angle, because in this kind of teeny zone it would not be possible to show the angle. All right, and in that case we will be able to compute this much area. We will be able to compute this much area, the upper portion only, starting from A to the point B up to the origin. This much portion would be possible to compute the area of this much portion. Okay, and if this area is multiplied by how many times? You see, this is 1, this is 2, this is 3, this is 4, this is 5, this is 6, this is 7, and this is 8. So 8 similar area is there. So if this area is multiplied by 8, then you will get the total area. That's why this is multiplied by 8. So 8 multiplied by the area under this curve, this much shaded area, that means O, A, B, again come back to O. Starting from O, then go to A, then through the point B, again come back to O. So this much area under the curve, that is actually represented by the integral half integral r square d theta, and there theta should vary from 0 to pi by 4. Hmm. So in this way we compute the total area, and afterwards just we put r is equal to a cos of twice theta. Hmm. And if this is just integrated, then ultimately you will get this area half of pi a square. All right, and these are the standard some examples. This is also there. R square is equal to twice a square cos of twice theta. In the previous question we had r is equal to a cos of twice theta, and in this question we have r square is equal to a square cos of twice theta, and this is the curve of the function represented by r square is equal to a square cos of twice theta. This is called lemniscate of Bernoulli, or simply the lemniscate. And I am just stating these results over here in this lecture. At least I am just stating the results, so you can go through this example, question number 4 as well. In this portion as an exercise, you can go through the questions of this question number 1 and this question number 2. You can also go through this kind of questions of this question number 3, but most of these questions have been solved in this previous solved examples. Got it? So that's all for today. Okay, then thank you for being with us in this lecture.